We continue our discussion of section 3.5. Today we will talk about applications of the fundamental theorem of arithmetic. Please take a look at theorem 6. We will not prove theorem 6. It's a hard to prove classical result. But let us look at what it says. Let a and b be relatively prime positive integers. So the greatest common divisor of a and b is 1. Then the arithmetic progression an plus b contains infinitely many primes. So let us discuss one trivial case of theorem 6. Let a be 2 and b be 1. Theorem 6 in particular says that there are infinitely many prime numbers of the form 2n plus 1. This is exactly what we have here. There are infinitely many prime numbers of the form 2n plus 1, where n is a positive integer. So we can easily prove a particular case of theorem 6 when a is equal to 2 and b is equal to 1. It is easy to prove this. To prove this result, we just note that there are infinitely many prime numbers and the only even prime number is 2. Since there are infinitely many prime numbers and the only even prime number is 2, the rest are odd prime numbers. There are infinitely many odd prime numbers. And we're done. Now let us discuss a significantly harder to prove particular case number 2. Here is example 2. Suppose a is 4, b is 3. There are infinitely many prime numbers of the form 4n plus 3, where n is a positive integer. In order to prove this result, first prove the following lemma. If a and b are integers, both of the form 4n plus 1, then their product is also of this form. Here's how we do it. Since a and b are both of the form 4n plus 1, there exist integers r and s such that a is equal to 4r plus 1 and b is equal to 4s plus 1. Therefore, a times b is equal to this. Now let us expand parentheses and factor out 4 here. Done. Observe that the expression inside parentheses is an integer number. Therefore, AB is of the form 4n plus 1 again. Now let us prove the main result. We will prove it by contradiction. Let us assume that there are only a finite number of primes of the form 4n plus 3. Let us list all these prime numbers. Let us denote the first prime number, which can be written as 4n plus 3 by p0. The first prime number of this form is, of course, 3. So p0 is 3, and then we have p1, p2, and so on, pr. All these numbers are prime numbers of the form 4n plus 3. Here is what we do next. Let us consider the following new number. 4 times P1, P2, and so on, PR, plus 3. Note that 3 is P0. So what is written here can be rewritten of the form 4 times P1, P2, and so on, PR, plus P0. Let us compare this number with the number that we used in order to prove that there are infinitely many prime numbers. Let us go back to one of our previous handouts over here. Folks, please take a look. Please compare this. And we used this construction in order to prove that there are infinitely many prime numbers. Compare this with this. Over here, we have the sum of two terms. Term number 2 is the number 1. Term number 1 is the product of all prime numbers. Of course, here we assume that there are finitely many prime numbers. Over here, we have a slightly different idea. We do not consider over here the product of all prime numbers of the form 4n plus 3. We consider the product of prime numbers starting from the second prime number. We do not include this one. So over here we start from P1. This is the second prime number of the form 4n plus 3. Then we multiply these by 4, and then we do not add 1 here. We add the first prime number of the form 4n plus 3. Why we need this construction? We will see it in a moment. But the point is, if we consider this, we will be able to get a contradiction. Note that we need a contradiction because we assume to the contrary that there are only a finite number of primes of this form. So consider this. Let us show that one of the prime factors of Q is of the form 4n plus 3. So once again, don't confuse factorization of Q and this expression. What we see over here is not factorization of Q. It's just some product. 4 times P1 times P2 and so on times PR. Now let us factor Q. Let us factor the whole thing. So over here we claim that one of the factors of Q is of the form 4n plus 3. Moreover, one of prime factors. Here is why. First of all, observe that any integer is either of the form 4n or 4n plus 1 or 4n plus 2 or 4n plus 3 by the division algorithm. So for any integer, there are only 4 possibilities. It is of the form 4n or 4n plus 1 or 4n plus 2 or 4n plus 3. Note that any factor of Q cannot be of the form 4n or 4n plus 2 because both 4n and 4n plus 2 are even numbers. But Q is odd because it is equal to even number plus odd number even number plus odd number is an odd number. So Q is odd. Therefore, Q does not have an even factor, because if Q has an even factor, Q is even, but Q is odd. So, conclusion, any factor of Q is either of the form 4n plus 1 or of the form 4n plus 3.
Could you repeat the last part if you don't mind?
So, since any integer can be either of the form 4n or 4n plus 1 or 4n plus 2 or 4n plus 3, and since Q is odd, for any factor of Q, there are only two possibilities. It is of the form 4n plus 1 or of the form 4n plus 3, because any factor of Q cannot be of the form 4n or 4n plus 2. Do you understand what I'm talking about?
Yes, thank you.
So, once again, any factor of Q is either of the form 4n plus 1 or of the form 4n plus 3. Let us prove that there is at least one prime in the factorization of Q of the form 4n plus 3. We will prove it by contradiction. Suppose there are no prime factors of Q of the form 4n plus 3. This means that all prime factors of Q are of the form 4n plus 1. But if any prime factor of Q is of the form 4n plus 1, by the lemma above, Q is of the form 4n plus 1. But Q is of the form 4n plus 3. And by the division algorithm, the remainder is unique. An integer cannot be of the form 4n plus 1 and 4n plus 3 simultaneously. Conclusion, there is at least one prime factor of Q of the form 4n plus 3.
Could you just explain briefly why Q cannot be in the form 4n plus 1?
Because it is of the form 4n plus 3. By the division algorithm, a remainder is unique. According to what is written here, we conclude that if we divide Q by 4, the remainder is 3. But if Q is of the form 4n plus 1, and we divide Q by 4, the remainder is 1. Does this make sense?
Yes, thanks.
Here is what we do next. So, at least one prime in the factorization of Q is of the form 4n plus 3. However, over here we have all prime numbers that are of the form 4n plus 3. So, according to what we just said, Q is divisible by at least one of the numbers from this list. Let us show that this is impossible. Here is why. First, let us show that Q is not divisible by 3. Here is how we do it. First, let us move 3 to the left. We will get the following. q minus 3 is equal to 4 times p1 times p2 and so on times pr. Now, if q is divisible by 3, q minus 3 is divisible by 3. Since the left-hand side is equal to the right-hand side is also divisible by 3. Cannot be. By the fundamental theorem of arithmetic, factorization is unique up to the order, but over here there is no 3. This number does not have 3 in its factorization. We got a contradiction. Q minus 3 is divisible by 3. This is not divisible by 3. We get a contradiction. Similarly, suppose Q is divisible by one of these prime numbers. In this case, let us move this to the left. We will get this. Now, since some pj from this list divides q, and since pj is one of these numbers, pj divides the whole expression. But this expression is equal to 3. We get a contradiction. pj is bigger than 3 and pj divides 3. So if q is divisible by 3, we get a contradiction. If q is divisible by one of these numbers, we get a contradiction. So if we assume that there are only a finite number of primes, we get a contradiction. Folks, we are done with this example. Any questions?
Sorry, where does I understand, well, actually, no, I don't understand. The contradiction part, like at the end, could you explain that again?
Yes. So over here, we say that q is divisible by one of these numbers. You agree with that?
Actually, wait.
Probably not. Okay. So please take a look. It's written at least one prime in the factorization of q is of the form 4n plus 3.
Oh, and that comes from the division algorithm, right?
No, give me a second.
Plus the
So
left.
we just proved that at least one prime in the factorization of q is of the form 4n plus 3. Do you understand why?
Yes.
Since over here we have all prime numbers of this form, q is divisible by one of these numbers. Agree?
No, I do agree.
You agree, correct?
Yes.
Now let us consider two cases. First, suppose that q is divisible by 3. We get a contradiction. Then let us suppose that q is divisible by one of these numbers. We get a contradiction. So on the one hand, q is divisible by at least one of these numbers. On the other hand, we show that if q is divisible by 3, we get a contradiction, and if q is divisible by one of these numbers, we get a contradiction. Therefore, what is written here is not true. Therefore, the opposite is true, means there are infinitely many prime numbers of the form 4n plus 3. How about that?
Yes, I understand now.
Any other questions?
Yeah, Professor,
Yes.
by doing this, haven't we proved that Q is also prime?
We do not prove that q is prime.
I'm more alluding to the result that we can calculate the next biggest prime by simple iteration then.
What do you mean by next biggest prime?
Because we have all of these forms P0 through PR of that are prime that are of form 4n plus 3, right?
Yes.
Then by this algorithm, we can say that we can just keep on plugging in these numbers into 4n plus 3 and keep on getting prime numbers.
What you are saying is actually not correct. Here is why. Note that we came up with the conclusion that Q is not divisible by any of these numbers thanks to the assumption that there are only a finite number of primes. Like, going back to this, Q is not divisible by any of these prime numbers, but it does not necessarily mean that this is prime. You see?
Okay, I see.
For example, okay, so yes, okay, here's an example. This is not a prime number.
Okay, cool.
Conclusion, this number is not necessarily prime. Next. Now let us talk about irrationality. Let us go back to one of our previous handouts. Over here, we proved that square root of 2 is irrational using the well-ordering property. And the proof was quite long. Then over here, we proved that square root of 2 is irrational once again, and now the proof is significantly shorter. Now let us discuss the following general result. Theorem 7. Let alpha be a real number that is a root of this polynomial. Please take a good look at this polynomial. The coefficient in front of x to nth power is 1. All other coefficients are integers. So, if alpha is a real root of this polynomial, then there are only two possibilities. Alpha is either an integer or an irrational number. Before I prove this theorem, let us jump to applications. As I said, we already proved that square root of 2 is irrational in two different ways. Here is the shortest proof. Note that square root of 2 is a root of the polynomial x squared minus 2. Observe that this polynomial is of this form because the leading coefficient is 1 and all other coefficients, actually just one remaining coefficient, 2, is an integer. Since square root of 2 is a root of this polynomial, there are only two possibilities according to Theorem 7. Square root of 2 is either an integer or irrational number. Obviously, square root of 2 is not an integer because it is greater than 1 and lesser than 2. Conclusion, square root of 2 is irrational. Done. Now let us prove Theorem 7. So, suppose alpha is rational. Then alpha can be written as a divided by b, where a and b have no common divisor. Of course, b is not equal to 0. Now, since alpha is a root of this polynomial, this is equal to 0 by definition of a root. Root means you plug in this here, the result is 0. So alpha is of the form a divided by b. We replace x here, here, and so on here by a over b. We get this. Since alpha is a root, this is equal to 0. Next, multiply both sides here by b to nth power. If you multiply this by b to nth power, the result is a to nth power. If we multiply this by b to nth power, the result is a to n minus 1 times b, and so on. Next, move this to the right and factor out b. Done. And now observe that according to what is written here, a to nth power is equal to b times an integer. Conclusion: a to nth power is divisible by b. And now, suppose b is not equal to plus minus 1. Then b has a prime divisor p. This means that p divides b. But according to what is written here, b divides a to nth power. Since p divides b and b divides a to nth power, p divides a to nth power. It's exactly what is written here by Theorem 1 from section 1.5. Since p divides a to nth power, by corollary to Theorem 2, p divides a. We get a contradiction. P divides b, p divides a, but from the very beginning, we assumed that a and b are relatively prime. So we assumed that b is not equal to plus minus 1. We got a contradiction. Conclusion: b is equal to plus minus 1. And now let us put pieces together. At the very beginning, we assumed that alpha is equal to a divided by b. We concluded that this is possible only if b is equal to plus minus 1. Means a over b is an integer number. So if we assume that alpha is irrational, alpha is integer, this is possibility number 1. Possibility number 2, alpha is irrational. So in total, we have only 2 possibilities. Either alpha is irrational or it's an integer number. We are done. Folks, do you understand the proof?
I don't think I follow one line of reasoning.
Yes.
That we proved that alpha, if it is rational, has to be an integer.
Yes.
I don't understand why that also proves that alpha can be irrational as well.
Because if alpha is not rational, it is irrational. For alpha, there are only 2 possibilities. Possibility number 1, it is rational. Possibility number 2, it is irrational. Over here, we show that if alpha is rational, it is integer. Conclusion: alpha is either integer or irrational.
So by supposing that alpha is rational and then showing that it's not irrational.
Once again, so for any real number, there are only 2 possibilities. alpha is either rational or irrational. Agree?
Yes.
So, if alpha is irrational, we are done. If alpha is rational according to what is written here, it is an integer, and we are done again.
Okay, then I guess my question is, why are we done if we assume alpha is irrational?
Well, we want to prove that alpha is either integer or irrational. So if alpha is irrational, we are done. If alpha is rational, it is integer, and we are done. Still don't see it? Okay, fine. So agree or disagree? For any real number, there are only two possibilities. It's either irrational or rational. Agree?
Yes.
But according to what is written here, rational means integer. Conclusion, for any real number alpha, alpha is either integer or irrational.
Okay, I think it clicked now. I'm pretty confident now.
Next, now applications. As we discussed, there are several ways of proving that square root of 2 is irrational. One way is to use the well-ordering property. Two other ways, and I call it method number 1 and method number 2, is to use various properties of divisibility. Let us actually go over. So we assume that square root of 2 is rational. We square both sides. We move b squared to the left, we get this. And now we can get a contradiction in two different ways. The shortest way is the following. Since the left-hand side is divisible by b, the right-hand side is divisible by b, so a square is divisible by b. But at the very beginning, we assume that a and b are relatively prime. Since b divides a square and a and b are relatively prime, b divides a by theorem 1 from this section, by this. We discussed this proof. So b divides a, therefore a over b is an integer, but square root of 2 is not an integer. Contradiction. Method number 2. Instead of using divisibility by b of the left-hand side, let us use divisibility by 2. The left-hand side is divisible by 2. Therefore, the right-hand side is divisible by 2. And one can show corollary 1 to theorem 2 that 2 divides a. Therefore, a is even. Or replace a by 2k. Done. Expand parentheses, cancel out 2. Conclusion, b squared is divisible by 2. Therefore, b is divisible by 2. So a and b are divisible by 2. We get a contradiction. But once again, the shortest way is to use theorem 7. Square root of 2 is a root of this. This polynomial is of this form. Therefore, there are only two possibilities for square root of 2. It's either integer or irrational. Square root of 2 is not an integer because it is between 1 and 2. Therefore, it is irrational. Let us prove that 1/3 times square root of 2 plus 5 is irrational. Assume to the contrary that it is rational. Let us rewrite this as this. Well, in order to rewrite this as this, multiply first both sides by 3, move 5 to the right, and modify a little bit the fraction. You'll get this. Note that square root of 2 is irrational. This is a rational number. We got a contradiction. Here is why this example is important. Note that in this case, in order to prove that this number is irrational, we cannot use Theorem 7 directly, because in order to use Theorem 7, the leading coefficient should be 1. However, one can check that this is a root of this polynomial, and the leading coefficient is not 1. So, Theorem 7 has its limitations. Theorem 7, according to this example, can be used in order to prove that this is irrational, this is irrational, this is irrational, and so on. But in this example, we cannot use Theorem 7 directly. First, we have to rewrite this as this, and after that, we apply Theorem 7 to square root of 2. Here is another example. Prove that square root of 2 plus square root of 3 is irrational. In this case, we can use Theorem 7 directly. However, we get another problem. This is a root of the following polynomial, x to 4th power minus 10x squared plus 1, and we cannot really come up with this polynomial easily. So, if we have just square root of 2, it is easy to find a corresponding polynomial. Square root of 2 is a root of x squared minus 2. But for this number, now it's pretty problematic. Therefore, the easiest way to prove that this is irrational is to assume that it is rational, square both sides, expand parentheses, 2 plus 3 is 5, square root of 2 times square root of 3 is square root of 6, move 5 to the right, divide both sides by 2, done. The left-hand side is irrational. Now we can use Theorem 7. The right-hand side is irrational. We get a contradiction. Here's another example. We can use Theorem 7 here, but look at this polynomial. However, we can assume that it is irrational, move square root of 2 to the right, cube both sides. These are still laborious computations, but these computations are easier than the process of coming up with this polynomial. So, Theorem 7 has its limitations. Lastly, it is fundamentally impossible to use Theorem 7 in order to prove that this number is irrational, because one can show that this number is not a root of a polynomial with integer coefficients at all. In other words, one can show that this number is transcendental. In order to prove that it is irrational, we use the following argument: assume to the contrary that it is irrational, and then erase 5 to the left-hand side and to the right-hand side. The right-hand side becomes 5 to the power a over b. Done. The left-hand side, 5 to this power is 2. After that, erase both sides to the power b. We get this. A left-hand side is odd, or right-hand side is even. We get a contradiction. Folks, any questions here?
Oh, I do have a question.
Yes.
If a number is an integer or a rational number, that does not mean that is a root of a polynomial, in that
of a
form.
polynomial of this form? No, absolutely not. Again, here's an example. This is irrational, but it is not a root of the polynomial where the leading coefficient is 1 and all other coefficients are integer numbers. Here's another example. As I said, this is irrational, but it is not a root of a polynomial with integer coefficients at all.